Hello and welcome to this revision session for AQA Physics Paper 3 on the Astrophysics option and the stars module of that option. So in today's revision session, what we're going to be looking at is examination questions for AQA A-Level Physics Paper 3, in particular the Astrophysics option and the stars module of that option. So if we've been successful and we've learned in today's lesson, we should be able to answer A-Level Physics examination style questions on stars, assess our understanding on A-Level Physics, in particular the stars module, and then finally understand what topics of the stars module we need to improve upon for AQA A-Level Physics. So how should you be preparing for revision in this particular session? Well, when you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this left hand side section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure you write your answers in full sentences and show full working out. In the right hand side section, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, how should you be revising A-Level Physics? So the first step is to learn the key facts. So use revision guides, class workbooks, student prep notes and the textbook to learn the key ideas of the course. You may wish to make mind maps or write out the notes yourself. Secondly, you may wish to test yourself by using things such as Caboodle, Seneca and Knowledge Checker to quickly test your own knowledge, which you may wish to do from your own cue cards. Then finally, you may wish to then practice by practicing examination style questions on things like exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work. Now, you may wish to download your own past paper examination questions to do that. So the three steps of learning the key facts, then testing yourself and then practicing exam style questions are how you should be revising. Now, in this particular revision session, you'll notice that we'll have three types of questions. The first questions we'll cover are the general check questions, which are the basic questions designed to probe your understanding on the key concepts of this particular topic. The second type of question we'll look at are checkpoint questions. These are more challenging questions designed to place your knowledge and understanding of the topics into different contexts and applications. And then finally, assessment point questions, which are past paper examination questions which mimic the type of questions found in public examinations. So let's now have a look at some questions on the stars topic of the Astrophysics option for AQA A-Level Physics. So the first question says, explain what is meant in astronomy by a parallax angle. Then a measurement of a parallax of a star 61 Cygni in the constellation Cygnus is found to be 0.316 arc seconds. What is its distance from the Earth in the following units? In parsecs, astronomical units and in light years. Then Proxima Centauri, a red dwarf 4.2 light years from the Earth is our nearest star other than the Sun. What is its distance from the Earth in parsecs and what will its parallax angle be? So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to be able to define what we mean by parallax angle. So the parallax angle by definition is half the angle between the direction of a nearby star from the Earth at one time of the year and then its direction from the Earth 6 months later, half the orbit later. Now in this next question, you've got to be able to convert from arc seconds from arc seconds into parsecs, and you do that by doing the distance in parsecs is 1 over the distance in arc seconds, so we get 3.16 parsecs. You've got to be able to convert between parsecs and astronomical units. There's a conversion factor given to you, so when you work it through, it's 650,000 AU, and then you've got the very famous conversion factor that 1 parsec is equal to 3.26 light years, so that works out to be 10.3 light years. Again, we can look at to work out the distance of Proxima Centauri using that particularly famous conversion factor, so it's 1.3 parsecs. And then remember, we can work out the parallax angle because it's 1 over the distance, okay, to the star in parsecs, and it gives you the angle in arc seconds. So it's 1 over 1.3, which is 0.77 arc seconds. The next question says, firstly, explain what is meant by stellar parallax, then calculate the distance from the Earth in parsecs to a star that makes a parallax angle of 0.18 arc seconds. Then use the data below to show the Earth is approximately 8 light minutes from the Sun, and then Proxima Centauri is around 1.3 parsecs from the Earth. So pause the video now, then unpause the video when you want to go through your answer. Right, again, let's go to the definition of parallax. Well, it's the technique used to determine the distance to stars less than 100 parsecs away from the Earth, and it's the motion or the apparent motion of nearby stars against the fixed background of the distant stars. Now, again, how can you work out the distance? Well, distance in distance in parsecs is 1 over the parallax angle in arc seconds, so it's 1 over 0.018, which is 56 parsecs. The next one, you can work out the distance from the Earth to the Sun as 1 astronomical unit, so it's 1.50 times 10 to the 11 meters. So therefore the time taken is going to be 1.50 times 10 to the 11, the distance, divided by the speed. First, for light is 3 times 10 to the 8, which is 500 seconds, which is approximately 8 light minutes. Then Proxima Centauri is around 1.3 parsecs from the Earth. Okay, so how can we then work that out? How can we show that? Well, we can work it through by saying it's 4.24 light years. We know the conversion factor, so we can then work out this distance in parsecs. The next question says, how much brighter is a magnitude 1 star compared to a magnitude 2 star? Then star A has an apparent magnitude of 3.44 and star B has an apparent magnitude of 5.72. Show that star A appears to be around 8 times brighter than star B. Then Aludra in the constellation Canis Major has an apparent magnitude of 3.5 and is 3,200 light years from the Earth. Calculate the absolute magnitude of Aludra. Then a type 1a supernova in a galaxy has a peak absolute magnitude of minus 19.3 and a peak apparent magnitude of 2.2. Calculate the distance to the galaxy in parsecs. So pause the video now, then unpause the video when you want to go through your answer. Right, so for this first one, you've got to be able to understand you can work out the difference in brightness by doing 2.51 to the power of the difference between the two magnitudes. So it's 2.51 to the power of 1, because that's the difference between 2 and 1. So therefore, it's 2.51 to the power of 1, which is 2.51. So the magnitude 1 star is 2.51 times brighter than magnitude 2, because the lower the number, the brighter the magnitude in this particular scale. The next one, you'll find once again the difference in the magnitude, so it's 2.51 to the power of 2.28, which is 8.2. The next one, you've got to use the equation, which is small m minus big M is equal to 5 log d over 10, where small m is the apparent magnitude, big M is the absolute magnitude, and d is the distance in parsecs. So the first thing you've got to do is use that conversion factor and change the distance from light years to parsecs, pop it into the equation, work it through, and you get minus 6.5. So it's going to be very bright because it's a very negative value. Then the next one, again, we're using the same equation again, but this time we're having to make d the subject. So how you can do that is remember to make log to the power, okay, one of the subjects, and then you can get rid of that log to the power by doing 10 to the power, so it would work through like so. So we get rid of that log value, so you can work through d is equal to 10 times by 10 to the power of m minus m over 5, pop in all the values, and we get to 200,000 parsecs. The next question says, using Stefan's law, compare the luminosity of one star with another that has, firstly, double the surface temperature in the same radius, then double the radius and half the surface temperature, then half the mass, the same density and 3 times the surface temperature. Then the Sun has a radius of approximately 700,000 kilometers and a surface temperature of 5,800 Kelvin. Calculate the energy radiated by the Sun during 1 year. Then the peak wavelength emitted by a distant star with a luminosity of 4.85 times 10 to the 31 watts is measured as 305 nanometers using a diffraction grating. Calculate the radius of this star. So pause the video now, then unpause the video when you want to go through your answer. Right, so this first one is using the Stefan's law and looking at how the factors link to each other. So Stefan's law is that the brightness or the luminosity is equal to sigma a t to the 4, ab and 4 pi r squared, because that is the surface area of a sphere, which we assume a star to be. So that tells us if we keep everything else constant but double the surface area, well therefore, okay, L will increase by a factor of 16 because it's 2 to the power of 4. The next one, we're doubling the radius and half in the surface temperature. Well, if L is proportional to t to the 4, if t halves, then L will decrease by a factor of 16, 2 to the 4. But L is proportional to r squared because a equals 4 pi r squared. So if r doubles, L increases by a factor of 4. So therefore, it decreases by a factor of 16, increases by a factor of 4. So therefore, the luminosity will decrease by a factor of 4. The next one, so if we look at the different ideas completely, L is directly proportional to t to the 4. So if t increases by a factor of 3, L will increase by a factor of 81, 3 to the power of 4. L is directly proportional to r squared. So if r decreases by a factor of 3 to the square root 2, because as mass halves, volume halves for a constant density, and volume is 4 over 3 pi r cubed. Therefore, L will decrease by a factor of 1.6. So that's 3 square root. That's 3 square root 2 squared. So therefore, what happens is if one increases by a factor of 81, the other decreases by a factor of 1.6, it overall increases by a factor of 51. This next one, we're going to use Stefan's law again. So that is brightness is equal to sigma A t to the 4, where A is 4 pi r squared. Okay, you pop in all the values, you work it through, and you get 3.95 times 10 to the 26 watts, because the luminosity, the brightness, is the power. So therefore, the power, we know, is equal to energy over time. So energy is power times time, or luminosity times time. So we multiply the luminosity value by the time in 1 year. So we work out the number of seconds in the year to do that. So we get 1.25 times 10 to the 34 joules. Then in this last question again, we're now having to use the Wien's displacement law. So lambda max times by t equals 2.93 times 10 to the minus 3. So we can work out the absolute surface temperature in Kelvin by working those through with those values. Remember, nanometers is 10 to the minus 9. So we get 9,800 Kelvin. We then pop it into the equation for Stefan's law, but we make R the subject. So we work it all through, pop in the values, and we get 8.59 times 10 to the 10 meters. So in our next question, it says calculate the Schwarzschild radius for firstly the Earth, secondly the Sun, third an average human being, and then fourth use the idea of escape velocity and kinetic energy and potential energy to derive the expression for the Schwarzschild radius. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, you've got to look for your equation for the Schwarzschild radius, which is the effective radius of a black hole. So the Schwarzschild radius is 2gm over c squared. So we can pop in all the values. Remember, g is a constant 6.67 times 10 to the minus 11. C is a constant 3 times 10 to the 8. Pop in all the values and you get your Schwarzschild radius out for the Earth, the Schwarzschild radius out for the Sun. Now, just to clarify, the masses of the Earth and the Sun are given on the equation sheet for AQA A-Level Physics. For an average human being, you're going to have to estimate what the mass could be, anywhere between 60 and 80 kilograms. I've used 75, so we get our answer out there. Now, how do we derive the Schwarzschild radius? Well, what we've got to say is, with escape velocity, when you've done this for gravitational fields, you can say that the kinetic energy is equal to the gravitational potential energy. Again, we can't use mgh for the gravitational potential energy because g, the strength of gravity, will change as you move through towards the black hole. So we've got to use big G, big M over R. You then pop in all your values. Remember, V will turn into C because we're looking at the speed of light, because that's we look to see if that can escape the black hole. Okay, and that's going to happen at the effective radius, because the fastest possible speed you could have. So you could then say half mc squared equals gmm over R. Small m cancels through on both sides. We then rearrange to make R the subject, and that is the Schwarzschild radius. The next question says, explain why the Chandrasekhar limit must be exceeded in order for the core to form a neutron star. The pulses received from LGM1 came from a pulsar 2.18 times 10 to the 19 meters from the Earth. Calculate the time taken for a pulse to travel from the star to the Earth. Then LGM1 is estimated to have a radius of 1.4 million times smaller than our Sun. Assume LGM1 has a density similar to that of a typical neutron star. Calculate its mass. So pause the video now, then unpause the video when you want to go through your answer. Right, so what is the Chandrasekhar limit? It's the idea that a mass must be large enough to provide a gravitational attraction strong enough to overcome this electron degeneracy pressure. So the neutron star will form at the Chandrasekhar limit because the electrons can't be squashed any closer together because they have their own integrity. So as a result, you need the gravitational attraction to be strong enough to overcome that degeneracy pressure. So therefore you've got your Chandrasekhar limit, that mass large enough to do so. This next question, again, it's a nice one because the pulses from pulsar are radio. Okay, so therefore it's going to be the speed of an electromagnetic wave, 3 times 10 to the 8. Time is distance over speed. You've got the distance, you've got the time, you've got the speed, so you can work out the time it takes to reach us. Now in this last question, we can work out the density. So density is mass over volume, and volume is 4 over 3 pi r cubed because we assume it to be a sphere as a star. So therefore our mass is going to be density times by volume. So you can put that that in together. So therefore we can work out what the radius of the star is going to be, because it's going to be 1.4 million times smaller than our sun. So you take the radius of the sun given to you on the AQA equation sheet and you work out the radius to be 400 meters. You can then pop that into the equation you just derived there and you get your answer out to be 5.2 times 10 to the 25 kilograms. The next question now says, in the 16th century, the astronomer Tycho Brahe made measurements of stars in the night sky. He measured the angle of a range of stars above the horizon. For each star, he measured the angle over a period of time to determine a parallax effect. Firstly, describe how the stellar parallax is used by astronomers. Tycho Brahe concluded that the Earth was motionless at the centre of the universe as he was not able to detect any stellar parallax. Suggest why he was not able to detect any stellar parallax. Tycho Brahe was one of the first astronomers to observe a supernova. Supernovas are used as a type of standard candle. What is meant by a standard candle? And then describe how standard candles can be used to determine the distance to nearby galaxies. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first one is explain what stellar parallax is. So that's a star is viewed from two positions at 6-month intervals, half the orbit of the Earth. So the star is viewed from opposite ends of the diameter of the Earth's orbit. So the change in angular position of the star against the backdrop of the distant or the fixed stars and galaxies is then measured. We can then use trigonometry to calculate our distance to the star with the right angle triangle. We can work it through to be the diameter of the radius of the Earth's orbit must be known for us to work it out because it's one of the sides of our right angle triangle. Now the next one, why detecting stellar parallax? Because those stars at the centre of the universe, which he thought was the point, were so far away that you couldn't determine any change in positions. They were too small to actually be measured with the naked eye in the 16th century. Now a standard candle, you've got to know the definition. It's a stellar object of known luminosity or known absolute magnitude. Now you can work out distances with standard candles, because if you can measure the intensity of radiation from the standard candle, you can work out its apparent magnitude, you know its absolute magnitude, so therefore you can work out its distance. The next question says, by what factor is a star of magnitude 1 brighter than one of apparent magnitude 3? The table 1 below shows a number of stars and their apparent magnitudes. Rank them in increasing order of brightness. How much is star the Canopus brighter than Altair? Then the sun has a luminosity of 3.90 times 10 to the 26 watts. What is its brightness in watts per meter squared at firstly the top of the Earth's atmosphere and then secondly at the surface of Pluto? So pause the video now, then unpause the video when you want to go through your answer. Right, so like we said before, to work out the difference in brightness, it's 2.51 to the difference in the magnitude. So it's 2.51 to the power of 2, so that is 6.3. Now, the order of brightness, the brightest object is the most negative number, and the dimmest object is the highest number. So the star should be ordered from most negative as the brightest to the least brightest, the dimmest at the biggest value. Now again, how much brighter is Canopus than Altair? So you do 2.51 to the power of the difference in the magnitudes, and it works through to be about 5.2 times brighter. Now in this next one, you'll have noticed from the equation it says in watts per meter squared. So to work out the brightness, you're going to have to take the luminosity of the sun, which is given to you, and then divide it by the area over which is over. So it's 4 pi r squared, because we're going to assume the ray is going to go as a sphere, and we know r to be the distance between the sun and the object. So we pop those into the equation and we get 1380 at the Earth, but at Pluto we get 0.88 watts per meter squared. The next question says, explain the difference in meaning between apparent and absolute magnitude. The star Procyon A has an apparent magnitude of plus 0.34 and is at a distance of 3.5 parsecs. What is absolute magnitude? The star Regulus has an apparent magnitude of plus 1.35 and an absolute magnitude of minus 0.30. What is its distance modulus? How far away from us is Regulus in parsecs? And then why is there a limit to the distances that can be measured using parallax? So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to know the difference between apparent and absolute magnitude. So apparent magnitude is the brightness of the object from Earth, while absolute magnitude is the apparent magnitude an object would have if it was located at a distance of 10 parsecs away from the Earth. Now the next question, we've got to use that equation, small m minus big M equals 5 log d over 10. Pop in all the numbers and you get 2.64. The distance modulus is that small m minus big M value that you can get. So you're just subtracting the two numbers, but remember you're subtracting a negative, so it's actually going to add, so therefore it's 1.65. The next one, how can you work it out? Well, you can then use that in that equation, m minus m equals 5 log d over 10, work it through, and we get 21.3 parsecs. Remember how to get rid of that log is going by 10 to the power. And then why is there a limit to distances that can be measured in parallax? Because as we said before, as the distance to an object increases, the parallax angle becomes smaller because the apparent motion of a star gets less, so therefore it looks like it isn't moving and can't be measured. The next question says the star Arcturus has a radius 25 times the radius of the Sun and a surface temperature of about 4,300 Kelvin. Estimate the luminosity of Arcturus. The star Rigel has a luminosity 66,000 times that of the Sun. If its surface temperature is 11,000 Kelvin, estimate the radius of Rigel, and then what is the peak wavelength emission of Rigel. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, we're trying to work at luminosity, so it's got to be Stefan's law. So it's sigma AT to the 4. So you pop in all those values. Remember, A is 4 pi r squared because it is this sphere. Remember, it's 25 times the radius of the Sun. Pop in all the values. It's 7.4 times 10 to 28 watts. Again, this next one, we've been given luminosity now. So at this point, we're rearranging the equation, making R the subject and working it through. So we get 5 times 10 to the 10 meters. And then the peak wavelength we can do with the Wien displacement law. Lambda max times by t equals 2.9 times 10 to the minus 3. Pop in all the values, work it through, and we get 2.6 times 10 to the minus 7 meters. The next question says, Sirius is the brightest star as seen from the Earth and has a surface temperature of 9,940 Kelvin. Calculate the peak wavelength emitted by Sirius and use this value to sketch a blackbody radiation curve for Sirius. Then Arcturus is the fourth brightest star as seen from the Earth and has a surface temperature of 4,290 Kelvin. Describe two ways in which the blackbody radiation graph will be different for Arcturus. So pause the video now, then unpause the video when you want to go through your answer. Right, so for this first one, you've got to be able to work it through what the peak wavelength would be by doing the Wien displacement law. So lambda max equals 2.9 times 10 to the 3 over t, so we get 2.9 times 10 to the minus 7, so that's about 300 nanometers approximately. Then you've got to be able to sketch what a blackbody radiation curve looks like. Now the blackbody radiation curve should have a peak which is shifted to the left hand side, but it's a continuous curve as shown, and it should peak at about 300 nanometers. Now what would happen if you have something with a lower surface temperature or a higher surface temperature? So what would happen is if Sirius has the higher surface temperature, it's going to have a bigger radiation emission because that's a law of radiation. So therefore what would happen is firstly the intensity would be higher for all the values for Sirius because it's given off more radiation. Okay, however the peak wavelength for Sirius would therefore be a lot shorter as well. So if we go back to Arcturus, the peak wavelength would be bigger, okay, than that of Sirius, but its intensity at all values will be much lower. The next question says, sunspots are cooler spots on the sun's surface that have a temperature of around 3,000 to 4,500 Kelvin compared with the average surface temperature of 5,800 Kelvin on the rest of the sun's surface. Use this information to explain why calculations using the inverse square law for the sun might be inaccurate. The data below gives some of the properties of the star Rigel in the constellation Orion. Calculate the peak wavelength in the blackbody curve of Rigel and calculate the surface area of Rigel in meters squared. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, it's an important idea you understand the assumptions of the inverse square law, and that is that you're assuming that the power output is constant throughout the process and also constant in all directions as well. This won't be the case because with sunspots the temperature is lower, so we know from the Wien displacement law that therefore if the temperature is lower, the power emitted by that particular star will be lower, so the inverse square law will not be true. This next question we're looking for peak wavelength, so we've got to use the Wien displacement law, lambda max times by t equals 2.9 times 10 to the minus 3. We work at all the values and we get 2.6 times 10 to the minus 7 meters. This next one, what we've got to do is we're trying to work out the surface area. So in this one we can use the Stefan's law, so we can say that power or luminosity equals sigma AT to the 4. A, we can therefore say, is the power or luminosity over sigma t to the 4. However, we've got to be able to work out what this power is first. So we've got to use the inverse square law, and the inverse square law says that the power will be the intensity multiplied by pi r squared, or pi d squared as I've written down there. Now what is d? The distance of this is going to be, well, you're going to have to work it through, so therefore it's the distance between us and Rigel, so we're going to convert that into meters if you want to work out a value in meters squared later. So we convert from light years into meters. That conversion is given to you on the equation sheet. You then pop it in to work out the power, pop that into the Stefan's law, so you get out 3.0 times 10 to the 22 meters squared. The next question says, firstly, explain what is meant by a parsec and draw a labelled diagram in support of your answer. Then Hipparchus satellite used the parallax method to measure the distance to more than 100,000 stars with the precision of 0.002 arc seconds. Calculate the distance in meters, the maximum distance measured by Hipparchus, and give the answer into the appropriate significant figures. Then the star Alpha Capricorni is in fact two stars that appear very close together. Some of the data about the two stars is summarised on the screen. Firstly, explain how the data in the tables indicates the two stars are not part of a binary system, and then explain why the angular separation of the two star changes when observed from the Earth during a 12-month period. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important that you can draw a labelled diagram of the right angle triangle produced to work out the parsec. So you'll notice we've got a right angle triangle there, and the distance between us and the actual star is given as a parsec. You know the distance between the sun and the earth below is going to be 1 astronomical unit. That's the definition of the astronomical unit. And then in that case, the angle produced for half of the particular half of the orbit is going to be 1 arc second. So you can see there in that particular diagram. In this next one, well, what did we know before? We said that distance in parsecs is equal to 1 over the parallax angle in arc seconds. So therefore it's 1 over 0.002 because that's the precision. So therefore we've got a precision of about 500 parsecs to work it through. Now we can put that into meters by converting from parsecs into meters. We get that conversion on the equation sheet, so it's 2 times 10 to the 19 meters. Now they're not part of a binary system because you'll notice they've got a very big distance between them. So as a result there are 178 parsecs apart, which is a massive distance. Now a binary system is when the two stars are co-orbiting each other, and they can't be co-orbiting at such a great distance, so they can't be a binary system. Now why does that change? Well, the more the amount of parallax you will get depends on the distance you are from the Earth. The further you are away, the less parallax effect you will get, so the more distant star, alpha 1, will not move as much as alpha 2. The next question says, Epsilon Arandi is a star 9.94 times 10 to the 16 meters from the Earth. It has a diameter of 1.02 times 10 to the 9 meters. The apparent brightness of Epsilon Arandi is measured on Earth to be 1.05 times 10 to the minus 9 watts per meter squared. Firstly, calculate the luminosity of Epsilon Arandi, then calculate the surface temperature of Epsilon Arandi, and then state any assumption made in your calculation. So pause the video now, then unpause the video when you want to go through your answer. Well, we're trying to work out the luminosity here, so what we can do is we can use our inverse square law because we've been given the brightness, so we know that brightness is equal to the luminosity over 4 pi r squared from the inverse square law. So therefore we can rearrange that and work out the luminosity by popping in all the values. Now again, remember, okay, that we can work out the value of r very carefully by looking at how far away it is from the Earth as shown there. So you can work out our luminosity 1.30 times 10 to the 26 watts. We can then work out the surface temperature by using Stefan's law, because we know that the luminosity is equal to sigma at to the power 4. Now we know that A equals 4 pi r squared, so we can pop it all through. We get 5150 Kelvin. It's also very important to note that you're given the diameter in the information, but the question wants you to use the radius because we're working out the area of the surface area of the star, so it's 4 pi r squared, so just be careful about that. Now the assumption we make is for Stefan's law to be true, it must be a black body emitter. We've also assuming that because we're using our equations that it's spherical, it's a sphere, and that also the surface temperature is uniform, so we can use the inverse square law. The next question says Bellatrix and Betelgeuse are stars in the constellation of Orion. Some of their properties are summarised below. Firstly, explain what is meant by absolute magnitude. Work out which of the stars is closer to the Earth. Explain your answer. Calculate the wavelength of the peak intensity in the blackbody radiation curve of Bellatrix, and then sketch the blackbody radiation curve for Bellatrix with a labelled wavelength axis with a suitable scale. So pause the video now, then unpause the video when you want to go through your answer. Right, learn the definition of absolute magnitude. It's the brightness of a star as it would appear from a distance of 10 parsecs from the Earth. The two stars, which one is going to be closer? Well, the answer is going to be Betelgeuse. Now you can see that because the Bellatrix has a much more negative absolute magnitude, it must be a lot brighter than Betelgeuse, but it only appears a bit brighter from the perspective of the Earth, indicating that it must be much further away because it doesn't appear to be much brighter than Betelgeuse, even though it should be a lot brighter, so therefore Betelgeuse must be closer. Now to work out the wavelength, we've got to use our blackbody radiation curve ideas to look at the Wien displacement of lambda max times by t equals 2.9 times 10 to the minus 3, pop in all the values, and we get 1.32 times 10 to the minus 7 meters. Now that tells us we can use our radiation curve because that's where the peak should be. It's steeper on the left hand side compared to the right hand side, and therefore it gives you a continuous spectrum as well. The next question says Table 1 summarises some of the information about 4 stars in the constellation Cassiopeia. Firstly, which star has the highest surface temperature, and then Figure 1 shows the intensity received at Earth from 2 of the stars plotted against wavelength. The effect of absorption by the Earth's atmosphere is not shown. Discuss what information can be found from Figure 1 about the temperature and the colour of these stars. Support your answers with suitable calculations. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can look at which one is going to have the highest surface temperature by looking at the colour of the star. So you've got to be aware that the bluest stars on the blue end of the spectrum have the highest temperature, and the ones on the reddest part of the spectrum have the lowest temperature. So therefore the answer is because it is blue. Now the next one, from this diagram, you can work out what the peak surface temperature is going. Sorry, the surface temperature is going to be from the peak wavelength. So you can use the Wien displacement law for each of them to work out what your peak wavelength of each of them should be. It's the peak wavelength, just the surface temperature of each star should be. Now you'll notice as well that from the information given from the peak wavelength on the graph, that shader has a longer wavelength than cap, so therefore if it's got a longer wavelength, that must be a redder because red has a longer wavelength, the blue has a shorter wavelength, so therefore you can work out what colours that they should be as well. The next question says Table 1 summarises some of the properties of 4 stars in the constellation Hercules. Firstly, define the parsec. You may wish to use a diagram as part of your answer. Then deduce which star is larger, Copernicus or Reticulus. One of the 4 stars has the peak in its blackbody radiation curve at a wavelength of 1 micrometer. Calculate the corresponding temperature for this curve. Explain which star produced the blackbody radiation curve described in question 1.3. Then which star has the brightest absolute magnitude, and then determine the absolute magnitude of Saturn. So pause the video now, then unpause the video when you want to go through your answer. Right, as I said before, you can define the parsec as it's the distance at which 1 AU will subtend an angle of 1 arcsecond, which is 1/3600th of a degree, or you could draw that right angle triangle with 1 AU with 1 parsec and 1 arcsecond on your diagram. Now, which star is larger? Well, you look at that, you can work this out from using Stefan's law, because we know we've got A in that particular equation. Now you'll see that both of them are in the same spectral class. Now we assume that when things are in the same spectral class, they have the same surface temperature. So therefore, they have the same apparent magnitude, but Copernicus is significantly further away. So you can see that from the information given to us. So therefore it will have the higher power output, so therefore it will have the brighter absolute magnitude. So to have the greater power output at the same temperature, it must have a greater area, so it must be bigger. Now the next one, again, we've got to use our equation for the Wien displacement law of lambda max times by t equals 2.9 times 10 to the minus 3 to work out our value. Now think about which star will produce that. Well, this comes from you being able to link the temperatures to the spectral classes, and you've got to memorize what those values are, and that is it must be in spectral class M if it has that particular surface temperature. So therefore the only one that's M is Raskell-Healthy. Now, which star's got the brightest absolute magnitude? Again, it's Rastelecki. Now, how you can think that one through is, look, it's a significantly further distance away compared to all the other stars. However, all the other stars have a very similar apparent magnitude of brightness on the Earth, so therefore it must be the brightest because it's the furthest away, yet they all appear as similar brightness on the perspective of the Earth. And then the last one, you can work out this absolute magnitude by using your equation m minus m equals 5 log d over 10. Luckily, in the equation d is given in parsecs, no need to convert. Pop in all the values and we get 1.3. The next question says, the table summarizes some of the properties of two stars in the constellation Ursa Minor. Using these data, describe and explain one similarity and one difference in the appearance of the two stars as seen with the unaided eye by an observer on the Earth. Then deduce which of the two stars is further from the Earth. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can think about firstly the brightness, and you can also think about the colour. So the first thing you can work out is the brightness is the apparent magnitude. So straight away, because they've got the same apparent magnitude, they'll appear the same brightness from the Earth. But the difference is going to be linked to their colour, which is linked to their spectral class. So you should hopefully know the differences by learning the colours of the spectral classes. So Cohab, because it's a class K, would appear orange or red. Polaris, because it's a spectral class F, would appear yellow or white. Now, how can you work out which star is further away? Well, again, you're given the radius of the star, and then you can work it through by the Stefan's law by doing P equals sigma AT to the 4. Now, both have the same area, but we can say that because Polaris is in spectral class F, we should know that has a higher surface temperature than K. That's just a fact you've got to learn. So therefore, it must have a higher power. So therefore, Polaris must have a greater power output, but they both appear the same brightness from the perspective of us on Earth. So therefore, Polaris must be further away from the Earth, so it doesn't appear as brighter than Cohab. Next question says, the summer triangle consists of 3 stars, Altair, Deneb and Vega. Some of the properties of the 3 stars are summarized in the table on the screen. The 3 stars belong to the same spectral class. State and explain which spectral class they belong to. Deduce which of the 3 stars appears the brightest, and calculate the distance from the Earth to the closest of the 3 stars. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to learn the temperatures and how they're linked to spectral classes. So it's spectral class A because that's the temperature range they all go into. Which will appear the brightest? Well, that's the one with the most negative apparent magnitude. So therefore it's Vega from the values given. And then the distance to the closest of the stars, well, you should work out that Altair is going to be the closest of the 3 stars. You can tell that because if you look at its absolute magnitude compared to its apparent magnitude, well, that's got quite a bright apparent magnitude perspective from the Earth compared to its absolute magnitude. Now you can see Deneb is very bright from 10 parsecs away, but from where it is on Earth it's much dimmer, so therefore it must be really far away. And then Vega has approximately the same apparent and absolute magnitude, so therefore it must be about 10 parsecs away. But Altair, because it's a lot brighter from the perspective of Earth compared to what it actually is 10 parsecs away, must be a lot closer to us than 10 parsecs, so it has to be Altair that's the closest. Pop in all the values, work it through, and you get 5.2 parsecs. Now, from this information again, deduce which of the 3 stars is the largest, and then calculate the wavelength of the peak in the blackbody radiation curve of Altair. So pause the video now, then unpause the video when you want to go through your answer. Right, so how can you work it through? Well, again, we're looking at area, so we've got to use Stefan's law again. So the answer is Deneb, because they all have approximately the same temperature, because they're all in the same spectral class. We can just assume the temperature is constant. So therefore, okay, Deneb, okay, has the highest absolute magnitude from the information given to us, so therefore has the highest power output. So therefore, it must have a much greater power output, so therefore it must be the largest of the stars. So therefore P equals sigma AT to the 4, because T is constant, the only factor affecting P is A, so therefore if the P is the highest, A is the highest. Next one, once again, we use the divine displacement law. Lambda max times by T equals 2.9 times 10 to the minus 3. We worked out to be 3.8 times 10 to the minus 7 meters. The next question says, during their life cycle, stars go through a number of stages. Betelgeuse is a red giant star with a luminosity of 4.49 times 10 to the 31 watts. The peak intensity of the radiation from Betelgeuse occurs at a wavelength of 850 nanometers. A website claims that the radius of Betelgeuse is 1,000 times the radius of the Sun. Assess the accuracy of the claim. The Hertzsprung-Russell diagram shows the position of some of the main sequence stars. Add the approximate positions of the Sun and Betelgeuse to the diagram. Mark the position with label crosses, and then state what is meant by a main sequence star. So pause the video now, then unpause the video when you want to go through your answer. Right, for this first one, what we're going to do is work out the temperature of Betelgeuse, and we can do that because we've got the peak wavelength. So we can use the Wien displacement law to work out the temperature of Betelgeuse. Then what we can do is we can work out the luminosity of both Betelgeuse and of the Sun. Well, it says here that we think that we can work it through. So we've got the luminosity of the Sun from the question. We can then work out the luminosity of Betelgeuse as well, and we can then equate the two of them, and then we can actually ratio the two values and work out the ratio of RB to RS from those values as shown on the screen. And when you ratio those two values, they're 991. That doesn't equal 1,000, so the claim is actually inaccurate. The next one, you've got to be aware where the stars go in the Hertzsprung-Russell diagram. The Sun, we know, has an approximate surface temperature of 5,800 Kelvin and belongs in the main sequence, so you can pop it in the main sequence part at that particular temperature, whilst we know Betelgeuse is a red giant, so must go in the red giant sector of this particular diagram. And a main sequence star, by definition, is a star which is carrying out hydrogen fusion in its core. The next question says, Table 1 summarizes some of the information about 4 stars in the constellation of Cassiopeia. State which star in Table 1 is the dimmest on the absolute magnitude scale. Calculate the absolute magnitude of Shadar. Then Chush has a mass over 15 times the mass of the Sun. Chush must eventually collapse to form a black hole. Calculate the radius of the event horizon for a black hole with a mass 15 times that of the Sun. So pause the video now, then unpause the video when you want to go through your answer. Right, the dimmest one is going to be the one with the highest absolute magnitude, and you can work that through because they've all got approximately the same apparent magnitude, the same brightness, okay, from the Earth. However, they've all got different distances. So Kapf, because it's the closest to us, okay, but they all appear the same brightness from the Earth, okay, must be the dimmest, and Ch must be the brightest because it's the furthest distance away. You can work out the absolute magnitude by doing the equation m minus m equals 5 log d over 10. Remember, d has to be in parsecs, not light years, so convert that, okay, and then you work it through to be minus 2. Then this next one, we've got to use a Schwarzschild radius, so RS equals 2gm over c squared. Pop in all the values. Remember, it's over 15 times the mass of the Sun. The mass of the Sun is given to you on the equation sheet, so you get 4.4 times 10 to the 4 meters. The next question says, Table 2 gives some data about the supergiant star Melnick 34 on the Sun. Calculate the power output of Melnick 34 divided by the power output of the Sun, that ratio. Then discuss why the evolution of a supergiant star in a local part of our galaxy could be dangerous for life on Earth. So pause the video now, then unpause the video when you want to go through your answers. Right, so in this first one, we need to work out the power output of each one. We're given the temperature, we're given the radius, we've got to use Stefan's law. Now remember, we can work out the area by doing 4 pi r squared for each one. So you can work out each one, ratio the two, and you get 3 times 10 to the 6. Now the next one, why could they be dangerous for life? Well, it's because when a star undergoes a supernova collapse and it forms a neutron star or black hole, it'll produce a gamma ray burst. Now the gamma ray burst can destroy the ozone layer of a planet such as the Earth, which would then be dangerous for life on Earth. The next question says, using the axis below, sketch the emissive power of a black body as a function of the wavelength for 3 temperatures, 1000 Kelvin, 1200 Kelvin and 1600 Kelvin. Indicate the temperatures on each curve. Wien displacement law can be written as lambda max times by t equals a constant. What does lambda max represent? Then obtain the value of the constant from the data booklet, 2.9 times 10 to the minus 3, and calculate lambda max for a temperature of 1600 Kelvin. And then assuming that lambda max for the Sun lies within the range of the visible spectrum, use the Wien's law to estimate the temperature of the Sun. So pause the video now, then unpause the video when you want to go through your answer. Right, this question firstly is testing your ability to remember a blackbody radiation curve. Now remember, for a blackbody radiation curve, the higher the temperature, the higher the curve will be for all parts of the line, but it will also have its peak shifted to the left hand side. So as you can see here, as the temperature increases, the peak shifts to the left, but the value for all of them increases as well. Now lambda max represents the peak wavelength of intensity. So it's not the highest possible wavelength of emission, rather it's the wavelength at which you get the highest intensity of radiation. Now the next one, we do lambda max times by t equals 2.9 times 10 to the minus 3, pop in all the values and we get lambda max to be 1800 nanometers. Now for this next one, you've got to assume that approximately the wavelength of visible light is about 550 nanometers. Pop it into the equation and we get about 5300 Kelvin. So that brings an end to our revision session in today's lesson. So hopefully, if you've learned in this particular revision session, and you can hopefully answer A-level physics examination style questions, you can assess your understanding on AQA A-Level Physics and understand what topics you need to improve upon for AQA A-Level Physics. So thank you very much for carrying out this particular revision session on the Astrophysics module for paper 3 of AQA A-Level Physics on the module of stars. Thank you very much and have a lovely day.